well, okay, we can start. So we again we met once more for project 3. So because so many of you actually had problems with APF navigation, especially with that part. So we'll go over the requirements once more, and I'll show a sample project which I picked from one of these submissions. Okay. So in this project, let's define the requirements once more. We were tasked to generate a world that has spawns obstacles and at some certain positions. We spawn our robots. And when we employ some path planning and navigation algorithms, right? So in part A, actually, you were already given the template code, which you only needed to change the file read format. So let's first read what we are talking about. I'll show the one of the sample codes. So we start by opening Gazebo. So we are running a different kind of version, the template code, which lets us, which reads parameters from a YAML file and spawns obstacles and robots, right? It has 2 obstacles. It has read its parameters and constructed the robot. When I came back to the terminal that I opened up Gazebo, I shall see that it subscribes the velocity command topic and advertises odometry values. That's important. Let's also check topic list. So this robot, Zacrophile, actually has camera modules on top, camera plugins. So in this format, you'll also see, you may also see topics related to vision, but here is the ones that we really care about. We process this mini robot, and it has velocity commands, and it publishes odometry values. And also there are some topics related to Gazebo itself. So Gazebo also lets us spawn models, or also it gives us the information related to those spawn models back. We can also use these topics as well, but since we have odometry input and we can publish velocity commands, we are good to go actually. So how to read from the YAML file? So the YAML file is actually here. YAML itself, as the name implies, it's not a markup language. It is more human readable format. Okay. So here we set goal, robot positions, obstacle positions, number of obstacles, etc. And also parameters related to navigation that should be read. You should read the YAML file from the, actually you can read it from the launch file itself. So see, if you employ a launch file, you can set this command so that it automatically transfers the parameters to the parameter server. Okay, but there are also other ways. So you can always come to the terminal and param load commands or load some certain YAML file. You can do that. And there is also a code version here. Where is it? So in this code, it gives the YAML file path here. Let me go to where the YAML file is. So this is the standard text read format, which we already provided. So the YAML file is actually, YAML read is here. It employs, again, a param load command. And once it is in the parameter server, I can assign a node handle, rows node handle, and get those values from the parameter server itself. So simple as that. Once I have it, the rest of the code was again provided to you. It spawns obstacles and spawns the robot. Once the robot is spawned, the associated topics should be seen as well. That part that was related to part A. So in the next part, once we have all the our worlds is set up, we need to implement a path planning algorithm of your choice. It could be either Ee451 or Dijkstra. So if you recall correctly, the Dijkstra algorithm is optimizing the cost, but with Ee451 we are also concerned about the goal heuristic itself, both the cost to get to some certain point and how the distance to that point to the goal is, they both affect our path planning algorithm. So most of you actually did this part well, with one exception though. So once you generate the path, which is a set of waypoints, we needed to show you need to show them not on terminal but the gazebo itself. So let's run this next part of the code so that I can tell it better. So once I run it, it generated the path, then it gives velocity commands to the topic and tries to move somewhere here, I guess, between the two obstacles. Okay. But actually, I do not see the complete path. The complete path is actually given here. You could do actually a few things here. So you can maybe spawn short, tiny obstacles, or you could spawn the robots at each waypoint one by one, so that you can visualize the path. These different visualization things could be done. Okay, but most of you did not prefer to do that. But in the latest part, which is the most problematic part, is we're moving towards the waypoints that our path planning algorithm provides. So what we needed to do here is set a next waypoint as next goal, and I should generate velocity, certain velocity commands so that I can move the vicinity of that goal. Whereas once I should always check where I am, and I should generate the next waypoint as my path point if I'm vicinity of some certain point. So here actually it completes its movements, and it publishes some certain parameters here. But let's see how it does in code. So actually our in the navigation package, the main code does simply open a constructor, runs a constructor of some certain class, then the work function inside that class, nothing more. So I should move here. So in the constructor, it has a certain parameter. It needs to read some sort of parameters from the parameter server itself. It reads all positions, obstacles, number of obstacles, and parameters related to the APF. Okay. So once we do that, let's go to the work function. So in the work function, you should see this subscription and publishing parts. We publish our data to this velocity command topic, and we get data from the odometry, and it runs a callback function each time data is given, data is and data enters. Okay, so the odometry callback function is okay. So the gazebo, we can get callback functions from gazebo. The mini gazebo package does actually this stuff. And in the end, I get my robot position at each instance. Okay, I know it. I know I can read odometry. I know where the robot is on my simulation. So let me go back. So the first thing I should do is, since I know where the obstacles are, I need to create an occupancy grid and run the Dijkstra or A* algorithm so that I can generate the waypoints to go, right? It should be, of course, it should work with different obstacle positions. So you should code it, not just write some certain occupancy grid, okay? So once I get the waypoints, so let's see, it starts from 0, goes to 1 in this format, okay? So this was where I was, this is my next goal, let's say. I should generate a velocity command so that I move towards the vicinity of this position. So the first goal is set. We are running an APF navigation command. So here we actually provided you empty functions for these, remember. So let's talk about what APF was really about. So we are actually imagining a surface here that has that our final configuration attracts us toward that point, and obstacles are repelling forces, and we are generating a force field. We are thinking about a force field, right? And then we move towards inside this field with a gradient descent algorithm. So it's basically it. So apart from the Greek alphabet stuff, the gamma part is actually related to attractive forces, and the beta part was related to repelling forces, right? The rest of it is actually mass, actually. The gamma is affected from how far our final goal point is. And the beta part is about the repelling forces and how far our obstacles are, so that we can we could set up if we can move freely or not. Okay. So the K parameter is actually an important parameter. Let me repeat it as well. With different K parameter settings, that means actually how forceful these attractive forces are. So if attractive forces prevail against repelling forces, that means I'll move more closely towards near obstacles. So it may be an unwanted scenario in, let's say, social navigation purposes. So a robot must not get too close to a person, let's say. But if the robot is moving in a warehouse, let's say, with no or a few humans, in that scenario, I could live with that. Okay, so it's actually kind of situational position. So what are good and what are bad about it? Since we are moving in a force field, it's really easy to obtain and relate it towards velocity and torque-based quantities. We can only represent obstacles. It could be run in a local map. We do not need the complete whole area map. And it's also reactive. So the obstacles change and trajectory also change. But since we are using the gradient descent, it can be stuck in the local minima. So in some cases, in some certain occasions, the robot may stuck or does not reach the goal, or it could move some stuttering movement towards or near the obstacles. Some unwanted scenarios could occur if you do not set up correctly your parameters. It's maybe, again, as we say, it's maybe hard to difficultly compute these forces correctly. And also, we are here representing obstacles with in circular formats, but most obstacles do not are not like that, right? So maybe it's hard to represent all obstacles with in a realistic format. So you either generate a few, let's say, 10 sphere obstacles for one obstacle or something like that. It's hard to actually represent it in a realistic way. Okay. So here we calculate attractive forces, the derivative of it, and the repellent part, and again its derivatives. You can also see them here. I'll let you compare them with your code as well. You can stop the video and compare what it does with your code. Okay. So once we got all this stuff, we need to relate it to velocities. We find the gradients and normalize it so that we can finally relate it to position change or velocity change. Okay. So once I got it, so it employs the grad velocity function, and it relates it with linear and angular velocities. It may be different limitations due to the robot. I guess a few of you sent feedback about the robot is harder to control and it falls down in some certain occasions. And in that scenario, you could limit the maximum linear and angular velocities. That's okay for this project. Okay. So once we generate velocities, you set the next position, some certain using that velocity and the current position, and compare if the goal is if we need to compare whether we are in the vicinity of the goal or not. So if we are close to the, let's say, goal number 1, the next goal point should be goal number 2. Okay, in that format, which is here. If goal is not reached, you employ APF. If goal is reached, you set next goal, and you can employ APF until everything is done. Okay. So you publish velocity message and set towards that position. At least for this project, these were the things you should be familiar with. Okay. So do you have any questions? Well, if not, most of you aren't online here anyway. If you have problems with it, you can always email and ask me some parts of it if you do not understand. We will also provide the template code to you, which will include a sample of APF navigation for your final projects. Okay. You can always get functions from implementation of the APF and use it in your projects as well, which we plan to give this course today or tomorrow, I guess. Then we can talk about more about your final projects.